Welcome back. The first week we went over epidemiology, the background and history of it, and current applications. And I'm guessing by now we're all a lot more familiar with WebCT and how to find our way around in it. So I hope things are going more smoothly for you.
This is the PowerPoint audio presentation for Units 2 and 3. There will not be another one next week, so this really will cover 2 weeks worth of units. And it is about biostatistics, or the art of never having to say you're sure. There's a fair amount of material in this, so let's go ahead and get started.
Here's the outline. Here's what we want to cover. Why do statistics? What's the importance of it? Why should we spend time on this? We're going to talk about categories of data and their appropriate graphical displays. We're going to talk about basic statistical concepts. A lot of this should be a review: mean, median, mode, etc., range, interquartile range. We're going to talk about standard deviations, hypothesis testing, beta, power, p-value, and confidence limits. I'm going to try to stick with things that I think will be practical and that you'll be running into as you evaluate clinical data. We're also going to talk about basic statistical tests, just a few selected ones. And I want you to know that there's a biostats resource, Dr. Pierre Nunez. Here's his cell phone number, and he knows a lot more about statistics than I do. So you can certainly start with me, but if there's something that you feel is pretty advanced, you can go directly to Dr. Nunez, or you can come to me, and I may end up sending you to him. So why do research? Here's some examples of how we describe data when we just see a few points. And if you haven't seen this already, you certainly will in your practice in your healthcare system, where there might be 3 points of data that look like this, and people call it a trend. It's an upward trend. This is a downward trend. This is a downturn. This implies, mind you, that something really significantly has happened here. Also might be called a setback. A rebound. A turnaround. Given any 2 data points, one will almost certainly be higher than the other. So how do we know what's significant when we see data like this? Well, we use statistics. Here's another example. If you look at this, I want you to think for a moment about which of these clinics, or which of these providers, at Clinic X, has the best A1C average in their patient population. At first glance, I think many of us would look toward the left at E and O there and think that those are the highest. You see this kind of thing happen all the time, and the assumption is that those have the highest averages. What about, for example, BB? That seems a lot lower. What I'm going to show you will convince you, I think, that BB is pretty much equivalent to E and O, although it does not look like that on this graph. This is a different view of the data. This includes confidence limits. For each sample that was done on individual providers, there are confidence limits indicating that the true value for the provider, it falls within these limits with 95% certainty, so that, for example, in E on the far left, it does cross the average, meaning that with 95% likelihood, the true value for that provider's population does include, or might be, at the average. We can see that the 3rd, 4th, and 5th data points from the left, after you get by E and O, so now we're looking at W, S, and V, those are above the 7.1. Their 95% confidence intervals don't cross it. Those are statistically significantly higher. Here's another example. Percent of high school seniors who smoke daily from 1992 and 1993. So it looks like there's a 10% relative increase in those who are smoking. And we tend to look at this and conclude that indeed there was a substantial increase in the percent of high school seniors, in this case, who smoke daily. Now take a look at the data a slightly different way. You've got 92 and 93 at the bottom, 17.3 and 19. But now if you look over the previous several years, you see that the number has been bouncing around between 18.1 and 19.6 or so, up and down. And now the change between 92 and 93 all of a sudden doesn't look as significant. Here's the same data in a graphical form, and again you can see that this does not look very significant, even though the last two data points toward the right are the ones that we originally saw, and it looked like a significant increase. Statistics help us figure out whether or not there is likely to be a difference in the population based on what we see in our sample. So we very often can't look at the entire population, so we look at a sample, and then we make inferences about the population based on that sample. Next we'll talk about some categories of data. Also we'll touch on some graphical displays that are used with them and some measures of central tendency that are used with them as well. There's discrete versus continuous data. Discrete are discrete categories, just as it sounds. Something like males and females would be discrete categories. Continuous are able to have fractions in the different data points. So you can have a fraction of an inch. So inches would be an example of a continuous data set, whereas you couldn't have a fraction of a gender, for example, so that would be discrete. There are nominal, ordinal, interval, and ratio types of data. Nominal are named categories. As I mentioned, the male or female, or you might have different drug types. Those would be examples of nominal data. And those are measured by a mode. That's the measure of central tendency, is what's the most common data point or data category. Ordinal is like nominal, except that it's in order. So you might have small, medium, and large. They're not. You can't have a fraction of one of those, so it's not continuous data. It's discrete, but it's in an order. And that measure of central tendency would be either the mode or the median. You could also use, because it's in order. So you could pick sort of the central point. Interval is like ordinal, except that there's equal intervals. So that's where you might have, between like small, medium, large, you can't really tell what the amount is between them, but if you had different decades of life, for example, that would be example of interval. And the measures of central tendency used with interval data are mode, median, and you can also use mean there. And then there's ratio, which is like interval data, except there's an absolute zero. So height, for example, would be an example of ratio data. And mode, median, and mean can also be used as central tendency there. Also we have this parametric and non-parametric. Parametric basically means normal, and we're going to touch on that in a little bit more detail. Here are a couple of examples of bar charts and histograms, and you'll see these in the text as well. You can have the discrete data on the left with the bar chart, and on the right number of urgent emails. This is also a type of discrete data. You can't have a fraction of an email, but you can line them up connected to each other, these different categories, as opposed to the different groups of medications with pain ratings, for example, on the left, where you have discrete bars. They're not connected, and that's intentional. When you have a histogram with a lot of columns, a lot of bars on there, then it makes sense to go to a line chart where you put a dot in the middle of each one and then you connect them. It's just a little bit easier sometimes to see than a large number of individual bars, and it gives you an idea of what's happening between the dots. It is an estimation, but it gives you a sense of what's happening along the continuum. This is a stem and leaf plot. It's yet another way to visualize the data. It gives you kind of a different picture of what the data looks like. The column to the very left lists the number of data points in each row. So in the first row there are none. There is none. The second row is there are 4 data points. The third row there are 9, etc. In the second row you see the 0, which is the first digit of a 2-digit number. So there, in this data collection, there are 2 5s, 1 7, and 1 9. The third row starts with 1 as the first of 2 digits. So let me advance to the next slide. This is the row that we're talking about. This is the first digit. And you can see there are 2 10s, 2 11s, 2 12s, 1 13, and 2 14s. So again, this just gives you kind of a general picture of what the data looks like. This is a box plot, and it shows you, among other things, the middle 50% of the data. That's what's in the box. That is also referred to as the interquartile range, because it's the data points that are between the, or rather contained in the second and third quartiles. The middle 2 quartiles is the interquartile range. So it gives you that, as well as the median. And then if you follow the lines outside of the box to the right and to the left, those take you out to the fences there, which are the 95th percentiles of the data. So that gives you yet another graphical representation of continuous data. A stacked box plot, you see these oftentimes in studies, and this shows you the numbers in various categories. In this case it's different groups, and how those groups are made up. So in group A, the number at the bottom is the proportion that is single. Above that is the proportion that's married, divorced, widowed, and common law marriages. So it gives you an idea of the makeup of the people in group A. Again, another way to look at the data. And pie charts you're probably very familiar with as well. Now we also talk about dispersion of the data, and there's different ways to measure that, and we'll go through some of those. This is a term that's used with ordinal, interval, and ratio data. And when we look at dispersion, we often talk about the standard deviation, which is a commonly used measure of the spread of the data. To understand that, I want to start by looking at the components, or how the standard deviation is calculated or made up. We can look at individual values and get a mean value. Then if we subtract the mean from each of the individual values, we get a sense of how much the values spread out from the mean. Those are deviations. We can then sum those up and divide by the total number of measurements, or total number of values, and that gives us an average deviation. How much does the average value differ from the mean, or spread out from the mean? We can then square those individual values minus mean values, the deviations, and we get a squared average deviation by summing those up and dividing again by the number of values. We do this because we want to keep positive numbers, and so rather than deal with negative numbers, we square them all. And then if you do that, you need to take the square root, because if you're having squared values, now you've got a different unit of measurement than what you started with. So then we take a square root to get it back to the original unit of measure. So this is how we figure out the standard deviation, or the spread of the data from the mean. We look at all of the individual differences between individual values and the mean, and kind of map those out. We do that by summing it up, getting the average, squaring it, and then taking the square root. The normal distribution looks like this, and I'm sure you've seen this before. This is the bell-shaped curve where most of the data points are within the first standard deviation, up or down. 2/3 approximately, or 68%, are within one standard deviation of the mean. 95% of the data or so is between two standard deviations of the mean, so plus or minus 2 standard deviations, and then about 5% or a little less is outside of those 2 standard deviations, either up or down. So when you get data that roughly fits this shape, we refer to it as parametric, or falling within the normal distribution.
This shows how the mean, median, and mode relate. This is not a normal distribution. If it's normal, the mode, median, and mean tend to overlap exactly. If it's skewed to one direction or the other, they tend to spread out. The mean, in particular, is very sensitive to outliers, to extremes, and for that reason, we tend to use median as a measure of central tendency if there are outliers, or if the data is skewed, such as in this case. Now I want to talk about hypothesis testing, but I want to start with the life stages of a research question that we're then going to sort of walk through to illustrate the hypothesis testing. So we might want to know, for example, or we might want to test the hypothesis that people in Wisconsin are really brainy. However, that's a little bit subjective, not very clear, not very precise, so it's a little hard to measure. So we might want to refine that a little bit. We could say residents in Wisconsin have a high IQ. Again, high IQ is a little subjective, so we might want to determine how we're going to define that. Here's a more specific question or issue. Residents of Wisconsin have higher IQs on average than the U.S. as a whole. So that's the hypothesis that we're going to be testing. We want to get some samples. We can get those samples from a variety of places. Some of them are more applicable to our question than others, or more valid. So, for example, we might take samples from a UW Dean's List. That may not be all that representative. We might get samples from those who think that a bug zapper and a 6-pack of beer is quality entertainment. That might not be representative either. Or we might want to get a random sample of Wisconsin residents. That would probably be the most honest way to try to answer or address our hypothesis and find out whether or not it's true. Let's say we do our sampling. We get a sample, we measure their IQ, we get an average of 122. The question is that significantly higher than average? So here on the bottom is IQ. N is 50, that's our sample size. We get an average IQ of 122. We know that the average IQ by design is 100 overall. However, we really don't know if an IQ of 122 is higher than average. That is, are the Wisconsin residents, on average, do they have a higher IQ than the U.S. as a whole? And based on this sample, we need to figure out if that's true. We might want to get more samples. If we did, it would start to look like this. Each of these would represent a sample of 50, and they might start plotting out like this. If we do that, I think you start to get a different idea of whether or not this initial value of 122 is statistically significant. Here's some more. It's starting to take shape out here. And more. Now you can see what looks like a pretty normal distribution.
with a confidence interval. That is, we can feel pretty confident that the true population mean, the mean of all of the Wisconsin residents' IQ, we can be 95% sure that that falls within these 95% confidence intervals. And you can calculate these confidence intervals for a variety of data points. Now, if we look at this illustration with a possible higher Wisconsin IQ distribution and the U.S. distribution here, then we look at the sample that we got, which was 122 average IQ, and where it is determines how likely it is to belong to one or the other of these distributions, to belong to the U.S. distribution or a hypothetically higher Wisconsin distribution. If the sample we got had an IQ here, for example, it would be more likely to belong to the U.S. distribution, and there would be a smaller chance that there actually is a different and higher Wisconsin IQ population. This is even more likely to be U.S., and there is less of a likelihood that there's a separate and higher Wisconsin distribution. So let's assume for a moment that the null hypothesis is true. That is, there is no higher Wisconsin IQ population, that it is the same as the U.S. population. Then the further out we go in one or the other of the tails of the U.S. population, the least likely we are to find data there. The less likely we are for a sample to be out that far in the tail. It's just not very likely because there's not very many people who have an IQ out that far. In fact, we can pick a point. In this case, hypothetically, it's at 120, and therefore to get our sample beyond 120, there's only a 5% chance. To go out beyond this level might be a 3% chance. So the further out we go, the less likely it is to find a sample that actually falls out there, again assuming that all of them fall within the U.S. population, which is the null hypothesis. This also becomes the chance of a false positive. That is, if the null hypothesis is true, then getting a data point or a sample data point out in this area that I've pointed to is, if we call that the point beyond which we're going to say, yes, Wisconsin residents have a higher IQ, then that really is the chance of a false positive. So when we say that alpha is 0.05, the 0.05 is the chance of a false positive result. And this would be a 1 out of 100 chance of getting a data point out this far. So again, we have this, our sample, and we need to decide where it is. Well, we get an idea that it's not very likely that this belongs to a U.S. population. We start to get the sense this is out there a ways. This more likely belongs to a different population, that of a higher IQ. So it starts to look like there really is a difference in this data. Now let's assume that there is a difference. So assuming that the null hypothesis is not true, that the alternative hypothesis is true, that there is a group of Wisconsin residents that have a higher IQ, same sort of reasoning. Depending on where a sample is, we can see that it's more or less likely to get a sample there. Here it's more likely because there are more data points there. Here it's a little bit less likely than in the mean area. And we can say that if the alternative hypothesis is true, then in this situation the data to the left of this line is the chance of falsely concluding that there is no difference, or a false negative conclusion. This is a beta error, it's called. And the chance is about 20% that if the alternative hypothesis is in fact true, that we're going to get a sample out this far. Now, 1 minus beta is the power. So we have the area to the left of the line is the chance of thinking that really there is no difference. The area to the right of the line is the chance of finding the difference, of correctly identifying a difference if there really is one there. So it's the chance of finding a positive conclusion if one really exists. That's the power. This is a very important concept because in studies that are negative, we want to know what's the power of the study. Was there very much power to see the difference? How likely were we to see a difference if there really was one? If we're not very likely to see it, then the study isn't as valuable. So what affects the power? What gives us greater power to see a difference? Well, it's the area to the right of that line. So how do we increase the area under the curve to the right of that line? I think you can see that increasing the number of people measured, or the number of people in the population, would increase the chances of finding a real difference. So increasing the sample size and the spread of the data makes a difference. Decreasing the standard deviation or narrowing the spread of the data would pull people to the right side of that line, increasing the likelihood of your sample being to the right of that line because there are more people there, so your sample is more likely to be in that area. This example illustrates the importance of power and the utility of it. This is a meta-analysis looking at breast cancer mortality related to being screened or not screened, and there are a number of studies that are looked at here. Relative risk is what was measured, so these were prospective studies, and the lines next to each study are the confidence limits of that study. So the more subjects that were in the study, the shorter the confidence limits, the more certain it was. The fewer subjects, the larger the confidence limits. If the confidence limits cross 1, that means 1 is just as likely, essentially, as any other value within that line, and a relative risk of 1, meaning there's no benefit, there's no advantage or disadvantage. A meta-analysis adds all of these up, so in effect it increases the subject number and increases the power of the study. So looking down at the bottom, there's a diamond without confidence limits. Actually, they would be there, but it's very narrow because there are so many subjects by adding all these trials together, and that now shows a statistically significant benefit, whereas very few of the individual studies did. Again, power, if we have a smaller standard deviation, it's more narrow, and more of it is to the right of that line. So, back to our original sample, 122, we can see the probability of that belonging to the US population, assuming that the null hypothesis is true, is about 0.027. It's not very likely, and by convention, we tend to say that if there's less than a 5% chance, less than a 1 out of 20 chance that the null hypothesis is true, then probably it isn't. It's more likely that there is a difference and that this belongs to a different distribution, in this case, a set of IQs that are higher in Wisconsin residents. So we would conclude from this that there is a statistically significant higher IQ in Wisconsin residents based on this sample. Now we're going to look at a few selected statistical tests, and we're going to go through these fairly quickly. T-test is student's t-test was named actually after someone who went by the pen name of student because he had a job that was actually involved with auditing, I believe, and didn't think that people would attribute a lot of credibility to him. So he went by this pen name. He was the first one to sort of describe it. But if we're going to look at the difference between two means, like in this case we have two samples, treatment group, control group, sample sizes of 25 with means of 98 and 102 and standard deviations of 6 and 8. So we wonder if these two groups are statistically significantly different. influence your judgment of whether or not the difference is statistically significant. So we kind of touched on some of those already. The sample size would make a difference. Remember, the larger the sample size, the higher the power, the more likely to see a difference. The difference between the means would indicate, a larger difference would indicate more likelihood of a statistically significant difference. And a smaller deviation would make it more likely that these would be statistically significantly different from each other as well, because the spread of the data isn't as much. So when we're looking at the difference between the two means, we use this t-test, and it's the difference between the means of the two samples divided by the standard error of the difference. Now, the standard error, as you can see by this formula, is really adding up all the standard deviations. It's kind of taking the average of the standard deviations. So the sum of the standard deviations divided by the sample size. And again, we do this thing with squaring it and then taking the square root in order to eliminate negative numbers and still keep the same measurement units. So same sort of manipulation as with the standard deviation. So if we take the difference between the means and divide by the standard error, we get this t value. Now, the t value is increased by sample size, and I think you can see by this formula that an increased sample size would decrease the size of the standard error by the denominator getting bigger in that standard error formula. So the standard error would get smaller, and therefore t would get bigger. So the t value would be increased by sample size. So what would happen with a larger difference between means? Well, looking at that top formula, I think you can see that if the difference between means is bigger, then t is bigger. What happens with a smaller standard deviation? Well, back down to the standard error formula, if the numerator is smaller, then that standard error is smaller. If the standard error is smaller, then t is also bigger. So it kind of goes back to our power. It's analogous to the power discussion. So increased sample size, increased difference between means, smaller spread of the data would all tend to increase the t value. Then you plot the t value. And the further out on the tail it is, the more likely it is to be statistically significant. So we can calculate a t value and then see how likely it is to fit with the null hypothesis that there's no difference between the groups, or whether it's out far enough to say, yeah, this is a significant difference. We can do a paired t-test, which is pairing people, like a before and after test, for example, would be a paired test. And that would reduce the variability between the two samples and would make the difference more likely to be statistically significant because there's less variability, so the standard deviation would be smaller. I just really want you to know conceptually that we can do a paired t-test, and that's more likely to find a difference. Analysis of variance is looking at more than two sample means. T-test is looking at two sample means. Analysis of variance, or ANOVA, is looking at more than two sample means. There's one-way ANOVA and a factorial ANOVA. One way is looking at one independent variable, and factorial is looking at multiple factors. Independent variable are those that affect the outcome. And oftentimes we're looking at many of those. So there are many things that affect coronary artery disease, such as cholesterol, hypertension, smoking status, family history, etc. So those would be independent variables. If there are several of those, then we'd probably do a factorial ANOVA, and if there's one independent variable, then we do a one-way ANOVA. This is an example of an analysis of variance, or ANOVA. These are pain ratings. There are 5 patients and 6 different drugs, or perhaps doses of a drug, and there's a value, then 6 different values for each patient, A, B, C, D, E, F. You can calculate a mean for each drug. You can also calculate means for the patient, overall mean as well. Now, I've got these formulas on here, but unless you really want to look at them and follow the algebra, I don't think you really need to worry about it. I think the next slide is really gets across the message that I want. The question that we're asking with the analysis of variance or ANOVA is whether the differences that we see between groups, in this case the different drugs, are significant. And if they are significant, those differences between the groups of drugs should be greater than the differences within a group of with one drug. And that's really what we're comparing. So the differences between the groups compared to the differences within a group. If those are the same, then the different drug groups are not having any effect. There's no differences between the different drugs. This table shows the sum of squares and the mean squares of between groups relative to within groups. And again, you would expect a large difference if there was a statistically significant effect. So what we do now, just look at the mean square column. To calculate this F statistic, we take the mean square between groups, divide by within groups. So the larger the difference, the larger the F statistic. And then we can plot that just like we do a t-value and see whether or not it's statistically significant. In words, the greater the differences between groups compared to the differences within groups, the larger the F and the more likely the groups are to be statistically significant. Now, regression analysis describes the degree of association between one or more independent variables and the dependent variable. And we've already covered the difference between dependent and independent variables. Okay, this is taking a look at regression analysis, and this probably looks familiar. You can find a best fit line when you've got points plotted like this. In this particular case, it's skin fold associated with blood sugar level. And you take the points and you find a best fit line by minimizing the distances between those points and the line. When you've found the minimal distances, then you've got a best fit line that you can describe by y equals mx plus b, and it's called a linear regression. Then you can predict what other skin fold measurements would correlate with in terms of blood sugar. If the dependent variable is dichotomous, there's only two possibilities, two categories, and it's not continual, then you do a log transformation on it and becomes a logistic regression analysis. And then the other thing you can do is do it in different planes. So instead of just looking at skin fold and blood sugar, you could look at body weight and blood sugar, or waistline and blood sugar. So you've got this line going in several different planes at the same time. That's called a multiple logistic regression. And it's nice because you can really kind of predict the outcome of these factors, or the effect of these factors on the outcome, and control for them. And we'll get into that a little more when we get into the clinical trials. Now a little bit on the chi-square test. We start with the 2x2 table, where we have truth, the disease either being present or absent, which is not the same as real life. This is a little more black and white than we would see if you're trying to diagnose somebody with rheumatoid arthritis, for example. You look at multiple different things, or depression, and it isn't necessarily black or white. But for the purposes of these calculations and the ones that we'll look at in the next unit, we do think of the disease as being either present or absent. And same with the test, being either positive or negative. So people would all fit into one of these quadrants. Here's an early reference to the 2x2 table, which I thought was kind of amusing, written in the 2nd century. Appearances to the mind are of 4 kinds. Things either are what they are, or are what they appear to be, which is true positives, or neither are nor appear to be, true negatives, or they are and do not appear to be, it's a false negative, or they are not, yet appear to be false positives. Rightly to aim in all these cases is the wise man's task, or the wise DNPs, I suppose. Here is some real data that we can look at. This is from a study published in 2000 looking at the diagnosis of anemia with ferritin. Ferritin is the test, and the truth is anemia as defined by a bone marrow stain being positive or negative. Focus in the top left quadrant where the subject has the disease, anemia, and also has a positive test. Now, if there's no relationship between the test and the disease, if there's no association at all, we can predict what the expected number would be just if it was random association. And that's what we're doing here. So what we do is we take the proportion of those with anemia who test positive. That proportion is 1001 over 2579. We multiply it by the proportion in that row of those who test positive, which would be 809 over 2579, and then multiply it by the total. So the proportion of the column you'd expect to see in that quadrant, and multiply that by the proportion in the row that you'd expect to see in that quadrant. Multiply that by the total. So you would get an expected number, and you can do that for all four quadrants. Again, these are numbers that you would expect if there was no association, so you can then compare those to the numbers that you actually get. This then shows you the estimated numbers or expected numbers compared to the actual observed numbers. If there are no differences between the expected and observed values, then there's no association between the test and the truth, the test and the disease. If there is a difference, then there is an association, there is an effect between the two, and you need to decide sort of which direction that effect is just by looking at the numbers. The way you figure out if it's statistically significant is you plug these numbers into a formula that basically looks at the difference between the two, calculates a chi-square value, plots it on a curve, and decides if it's out far enough to call it statistically significant. If it's enough of a difference that you would expect that it's statistically significant. Same as with the other types of tests that we're talking about. And chi-square is used when looking at proportions. When you're looking at those with and without positive test, with or without a positive disease. These are some alternatives to the chi-square. Fisher's exact test when the frequencies are low because the chi-square doesn't work as well. And then the McNamara test when the variables are paired. Just really wanted you to hear those names. Okay, the final thing in this long unit, and I know it's been a grueling one, is I want to touch on the run charts and control charts. This is the data we looked at the beginning of the unit. This is the percent of high school seniors who smoke daily, and remember we saw that it didn't change much over time. And this is a run chart where you can follow something over time. So the way you construct a run chart is you plot a sequence of data over time, and usually at 15 or more data points. You look for significant trends, so 6 or more consecutive increases or decreases. So remember we started with wondering about how do you tell if this is significant or not? When is there really a statistically significant trend? Well, if each data point, if it's random, if it would have an equal chance of being above or below the prior one. And so if it's above the other one several times in a row, it's less and less likely. It's like flipping a coin and getting heads 6 times in a row. So statistically, that comes out to a fairly low number. You can figure it out by multiplying 0.5 times 0.5. Doing that 6 times would give you the actual chances of this occurring, but by convention, people feel that 6 or more consecutive increases or decreases means there's a significant trend. It's not very likely to have happened by chance. There's something that caused it. You can also look for 8 or more points above or below the median. So you can plot these 15 points and then draw a line that represents the median and look for 8 points above it or 8 points below it. So that indicates that there's some change, something that's keeping it away from the middle, keeping it above the median. You can also look at the number of runs above or below the median, and if there are very few of them, run being just a number of points above or below the median. If there are not very many changes, then the changes are more likely to represent a special cause, meaning that something actually caused it. It wasn't just random. If it was random, you'd expect there to be a lot of runs above and below because it would vary a lot. Okay, and then here's a control chart. We were talking about run charts, but control charts actually plot out the 95% confidence limits. And if the numbers that are sampled are the same over time, then those confidence limits or control limits will be stable. Sometimes you see these charts broken up because each time a different number is sampled, a different number in somebody's patient panel, for example, and then it might actually go up and down, be wider or narrower depending on the size of that sample. But if you look at this, then there's one point that goes outside of the confidence, the control limits, which are the same as confidence intervals, and so that looks like a special cause. It looks like, as we follow along, we see the green arrow there. That's out of the control limits, and it's considered to be a special cause. Something probably happened there to affect this.
Alrighty then, you have finished the PowerPoint audio presentation for Units 2 and 3 for biostatistics. There will not be another one next week. Next week we will be continuing Units 2 and 3 with biostatistics, but there will not be another PowerPoint presentation. Not until the following week, week 4, which will also be Unit 4. That's it. Have a great day.